Hello physical sciences and natural sciences students, welcome back to another lesson with me, Miss Martins. Today we'll be looking at balancing chemical equations. If you haven't subscribed to my channel yet, please do so now. I do math videos, I do science videos, I do exam practice videos. So hit that subscribe button and don't forget to give this video a thumbs up if you like the video and if you learned something. Let's jump right into balancing chemical equations. Now, the first thing that you need to know, and this is very simple, but I just want to make sure everybody starts on the same page as me, is that what you see on the screen is an example of a chemical reaction. And this is a balanced chemical reaction. Now, chemical reactions are represented with reactants on the left-hand side, an arrow, and products on the right-hand side. Okay, so these two things, hydrogen gas and oxygen gas, react. They chemically react. There's a chemical change, a chemical process. The bonds are broken, the atoms are rearranged, and a new molecule or compound or several molecules and compounds are formed. In this case, it's just one. We've got H2O. And the properties of the compound are completely separate and different to that of the reactants. But it's always the same. Reactants on the left-hand side, products on the right-hand side, separated by an arrow. Now, you need to know why we balance. The reason why we balance is because a chemical reaction, which is represented by a chemical equation, is an example of chemical change, not physical change. So physical change would be, for example, an ice cube melting. That's gone from solid ice to liquid ice, but we haven't made any new compounds. Chemical change, however, takes one or two or three or more reactants. We break those bonds, we rearrange those atoms, and we form new products. And when we have a chemical reaction, we need to make sure that there is a conservation of atoms and mass. Now, what does that mean? Conservation of atoms and mass. So to conserve means to keep the same, so stay the same, of atoms and mass. That means that if I have two hydrogen atoms in my reactants, I need two hydrogen atoms in my products. I can't just have two in my reactants and then have four in my products. Where did those extra two come from? And the reason why this is important is because it needs to obey the law of conservation of mass. So any chemical reaction, the mass of the reactants equals the sum of the mass of the products. It's very important to note that matter or mass cannot be created or destroyed, but rather it's transformed from one form into another, which is why, for example, when I react hydrogen gas with oxygen gas to form water, H2O, we formed H2O and now we have two hydrogens and one oxygen. But if you look at what we had on the left-hand side, we had two hydrogens and we had two oxygens. Do you see what we had? We had two oxygens, two hydrogens. Now, when the bonds were broken, when they rearranged themselves and made a new product, now there's only one oxygen. Now, the law of conservation of mass says, listen, that's not possible. Matter can't be destroyed. It can only be transformed from one form to another. So what that means is I need to multiply my oxygens by 2. And that's why we put a big 2 over here. But now it means we have 4 hydrogens over here. Because if I multiply this molecule by 2, it also affects the hydrogen, which means I also have to multiply that by 2. So now the oxygens are balanced. They each have 2, the reactants and the products, but now the hydrogens, there's 4 of them on the right-hand side, and only 2 of them on the left-hand side. But matter cannot be created or destroyed, so we have to multiply this one by 2 as well. And that's why we put a big 2 over there. So that is the reason why we balance. And I gave you another example over here. So I said, see how at the moment, the mass of the reactants is not the same as the mass of the product. So what I mean by mass is molecular mass, molar mass. I use the big numbers on the periodic table called the atomic mass numbers, and I work it out for the reactants versus products. So the atomic mass number of hydrogen is 1, and I multiply it by 2 because there's 2 hydrogen atoms over here. So we get 2 over here. And then 16's atomic mass number is oxygen's atomic mass number is 16, and I times it by 2 because I have 2 oxygen atoms, so that's 32. So for my reactant, I have 34. Okay, that's my mass of my reactants. But if you do the same for the products, you only get 18. That means that matter was not conserved. That means that mass was not conserved, and this is not possible. Now I've taken my balanced chemical equation. Can you see that it is now balanced? We can tell by seeing the big numbers in front of some of my compounds. I now worked out the mass again. So you see hydrogen has an atomic mass of 1 and I multiplied it by 4 because there's 4 hydrogens on the reactant side. 2 times 2 is 4. Okay, then oxygen, I said 16 times 2 because I have 2 oxygens. I get 36. That's the mass of my reactants. Now I did the same for my products. Again, 1 times 4, that is the mass of my products, my hydrogen in my products, 2 times 4. And then for my oxygen, remember that 2 applies to that oxygen as well. So 2 times 16 is 32 plus 4 is 36. There we go. The mass of my reactants is the same as my mass of my products. So that is why we balance. Now, it's very difficult to give rules for balancing equations or steps for balancing equations. So I know my students often ask me, ma'am, what are the steps? What do I do first? What do I do next? And the truth is that it's different for every equation. And a lot of the times it is a process of elimination. You try something, you count the atoms, it doesn't work, you erase it. Which is, I guess, why tip number 1 is always balance in pencil. Okay, always try and balance your things in pencil first and see if it works out. But to try and make it a little bit easier for you, I've written down some things that you need to remember and things that you can try. I do have some tips coming in later in the video, so make sure you watch so you can get those tips. So first of all, these are kind of rules that I came up with. You need to do these in order to get your balancing chemical equations right. Now, number 1, this is important for beginners, but as you practice and as you get better at balancing equations, you don't need to actually write down how many atoms of each element there are on the left versus the right hand side. So I'm going to show you a method where you do this. Kind of like what I did in the first example, but if you get better at this, you don't need to write it down each time. So I said that you can use inspection, which is what you do when you start improving your balancing skills. Oh, and another thing, guys, balancing takes practice. So you have to practice it. The more you do it, the more skilled you'll become at it. You'll see things that you struggle to see in the past. I hope that makes sense. Okay, but a massive rule is that when we balance, we add coefficients, which are big numbers, okay, to equal the number of the atoms on the left and on the right. So again, with my water example, remember it was hydrogen gas plus oxygen gas gives me water. Now I know that I have 2 oxygens here, and I know that I only have 1 over here, but we never, ever, 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 ever add a little baby number over here. We never add small numbers. We only ever add big numbers, coefficients. Okay, we can never change the number of atoms. So water will always only have 1 oxygen atom. But I can put a big 2 over here, which tells me that I now have 2 water molecules. And because I have 2 water molecules, I have 2 oxygen atoms. And now the oxygens are balanced. And then 2 times 2 is 4 hydrogen atoms. Here I've only got 2. Again, we can't tamper. We can't change this number. We have to put a big 2 there in order to make 4 hydrogen atoms. Okay, that links to rule number 3. Never change or add small numbers, only big numbers, and always use the simplest ratio at the end. So now what that means, let's say you've balanced this equation and that's your final answer, or at least you think that's your final answer. Always just double check your work, because what you're telling me is that the big numbers, so if you can see the big numbers over here, I've got a 2, a 4, a 2, and a 4. And if you check your work, it does make sense because it tells me that there's 2 carbons on the reactant side and 2 carbons on my product side. For my hydrogens, I've got 8. 2 times 4 is 8. And my hydrogens over here, I've got 4 times 2, which is 8 hydrogens. My oxygens, I've got 4 times 2, which is 8. And my oxygens over here, 2 times 2, which is 4 oxygens in this molecule over here. Well, in this section over here. And then 4 times 1, which is 4 oxygens here. 4 plus 4 is 8. So it looks like it is balanced because my carbons are balanced, my hydrogens are balanced, and my oxygens are balanced. But I hope that you guys have noticed the following. look at the big numbers. 2, 4, 2, 4. 2 to 4 to 2 to 4. Can I not simplify this ratio? Yes, I can divide the entire ratio by 2. So that is 1 to 2 to 1 to 2. Okay? So if you're going to balance properly, your final reaction should actually be, instead of a 2 over here, it should be a 1. So CH4 plus, instead of a 4 over here, it should be a 2. Instead of a 2 over here, it should be a 1. And instead of a 4 over here, it should be a 2. Now it is balanced properly. Okay, I hope that makes sense. If you don't believe me that it's balanced properly, you can take the new version that I've written out, count the number of carbons, hydrogens, and oxygens on each side. So for the reactants and for the products, and you'll see that it is balanced. So back to that rule. It says here, always use the simplest ratio at the end. Okay, let's do a few examples. Now what I'm going to do in my examples is I'm going to take it very slowly. I'm going to write out everything like I said in my rules. I said here, write down how many atoms of each element there are on the left versus right hand side. I'm going to do that, even though you might be able to do this already. You might be able to use inspection to do this, which is fantastic. That is what we're aiming for, but we all have to start somewhere, and we're going to start simple. So we've got Fe, we've got iron, and we've got iron on that side. Good. If there's something on the one side, it will be on the other side, okay? Because of the law of conservation of mass and atoms, number of atoms need to be conserved. We've got oxygen on the left, oxygen on the right. So now I have 1 iron and I have 2 oxygens. Over here, I have 2 irons and I have 3 oxygens. Now, I can already see that if I have 2 on this side and 3 on this side, I almost have to find the lowest common multiple for them in order for this reaction to balance properly. So 2 and 3 both go into 6. So I'm going to multiply this by 3 and I'm going to multiply this by 2. I hope you're with me, because if I multiply this by 3, I'm going to get 6 oxygens by here and 6 oxygens here. Okay, so whatever you multiplied with, that's the big number that we're going to put in front. Now remember, just because I am putting a 3 here now doesn't mean that this is the final answer. I may have to cross it out and try something else. That's just how balancing works, okay? It's sort of a process of elimination. And here I put a 2. Okay, now the problem is, by putting a 3 on this side, I haven't done anything else. I've just affected the oxygen. But by putting a 2 in front of iron 3 oxide, by putting a 2 in front of this whole compound, I've affected not only the number of oxygens, which was my goal, but I also affected the number of ions. Okay, so the big number applies to both of these atoms. That is why I can go 3 times 2, 2 times 3, to give me 6 oxygens. But now I've also affected the number of ions for my products. 2 times 2. Okay, so now I have 4 ions on my product side, and I only have 1 on my reactant side. But this is a nice easy fix, especially because iron is standing alone. So I'm just going to multiply this by 4 as well. So I'm going to put a big 4 over there. And now my equation is balanced. Always remember to just check your final ratio. So it's 4 to 3 to 2, which is as simple as it can get. So I know that I've balanced correctly. Let's do another one. In this reaction, I have hydrogen gas reacting with nitrogen gas to produce ammonia. Again, I'm going to take it nice and easy, and I'm going to divide my page into reactants and products. I've got 2 hydrogens on this side, 2 nitrogens on this side. On this side, I've got 1 nitrogen and 3 hydrogens. So now, what I'm going to do first is I know, I have 2 nitrogens on this side. I have 1 on this side. I could maybe put a 2 here. And if you think about it, that kind of works for the hydrogen as well, because I have 2 on this side and 3 on this side. And again, 2 and 3 both go into 6. So if I had to multiply this here by 2 to make 6, and I had to multiply this hydrogen over here by 3 to make 6. That kind of works. And then I'm going to put a 2 over here in front of nitrogen as well, because remember, the big 2 affects the number of hydrogens. So 2 times 3 gives me 6. And the number of nitrogens. So now I have 2 nitrogens on this side. And I have 2 nitrogens on this side. So we're good with the nitrogens. But now that I've added the 2 in front of this molecule over here, 2 times 3 gets me 6. So I need to make this one become 6. So I need to also times it by 3. That's also a nice, easy one. Okay, and again, our ratio is 3 to 1 to 2. So that's as simple as it gets. And I just wanted to show you guys over here, I have 6 hydrogen atoms in total on the left and the right. I have 2 nitrogen atoms in total on the left and the right. So the number of atoms is conserved. The mass of the reactants is also conserved. 6 times 1 plus 14 times 2. Now you might be wondering, ma'am, where are you getting these numbers from? Well, remember 6 is the number of hydrogen atoms, 3 times 2. And 1 is the atomic mass number of hydrogen. And 14 is the atomic mass number of nitrogen, and there's 2 of them. Okay? And then I did the same for the products. So mass is conserved, number of atoms is conserved, and we know we have done it correctly. So if they say use the law of conservation of mass to show that mass was conserved, this is what you would do. Okay, you get the mass of the reactants and the mass of the products. And this falls under the section known as chemical change. Now, for some tips. Now, these tips won't always work, okay? They're kind of guidelines. They're kind of there to help you. Most of the time, they do make things a little bit easier. So I wrote balanced atoms present in a single molecule of reactants and product first. I'm going to explain what that means now, but sometimes basically in a chemical reaction, we can have oxygen appearing in multiple products. Like in this example over here, we've got zinc sulfide reacting with oxygen, and there's oxygen over there, and there's oxygen over there. So because oxygen is in multiple products, we're going to balance. So because oxygen is in multiple products, we're going to balance that last. We're going to balance atoms present in a single molecule of reactant and product first. So a good thing to start with here would be zinc or maybe sulfur. Right, here it says balance oxygen and hydrogen atoms last. Usually in a reaction, these are the ones that make it easier if you balance them last. Not always, it depends on the reaction, but see if it works if you leave oxygen and hydrogen atoms till the last. And then I wrote here, treats polyatomic ions as a unit. So a polyatomic ion, for example, is something like the carbonate ion, or the sulfate ion, or the nitrate ion. So you'll see them in certain equations, such as this one. Here's a sulfate, SO4. Here's a sulfate. We can treat these like one unit. So on this side of the equation, in the reactant side, we have 1 of them. On this side of the equation, the products, we have 3 of them. Sometimes it's easier to treat it like a unit. So I would multiply this one by 3, okay? But now you've impacted the number of coppers, okay? So you might have 3 of the sulfate ions, but you also have 3 coppers, so we can put a 3 over there. Now we have 3 coppers here and 3 coppers there. But are the aluminium atoms balanced? No, I have 2 over here and I only have 1 over here. So I put a big 2 over here. And then we can check if it's balanced. I have 2 aluminiums on this side, 2 aluminiums on this side. Copper, I have 3 on this side, I have 3 on that side. You can break up sulfur and oxygen if you want, or you can look at it as a unit. I have 3 sulfurs on this side. On this side, I have 3 sulfurs. And you might say, ma'am, wait, how do you have 3 sulfurs on this side? There's the S. Let me just erase these brackets so you can see clearly what I'm talking about. Not the brackets, the scribbles that I made. There we go. There's the sulfur. And outside the brackets, there's a 3, which means I have 3 sulfurs. Oxygen, I have 4 times 3. I have 12 oxygens. Same thing over here. I have 4 times 3. I have 12 oxygens. And there we go. We've balanced it. Easy. So by treating the polyatomic ions as a unit, it helped me to balance that chemical equation. Okay, so let's take keep the other tips in mind when we do the next example. Remember, we're going to try and do hydrogen and oxygen last, and atoms that are in multiple different molecules of reactant and products, we're also going to leave till last. So like I said, over here, we see oxygen over here and oxygen over here, so we're going to leave that last. Starting with zinc. My zinc already balanced, 1-1. My sulfur already balanced. So in this case, you can see immediately the tip won't work for this one. Immediately, I have to look at the oxygens. Now, the oxygens are a little bit of a pain in this one because I've got 2 on this side. Okay, I've got 2 here. And on this side, I've got 2 plus 1, which is 3. So a nice first step would be to put a 2 over here. And the reason why is because then we make the number of oxygens even. Okay, so what I did is now I have 2 oxygens here plus 2 over here. I have 4 oxygens on the right hand side. Making it even helps me out because I know that I have 2 on this side. So if I put a number here, then I can maybe match that number over there. If I had to put a 2 over here, so let me just show you the alternative. If I had to take that away, if I had to say, okay, I have 2 oxygens over here, that means that if I had to see, we can't put anything here that will make this equal 3. If it's 2 on this side, what am I going to put here to make this equal 3? It's not going to work. So then if you said, okay, cool, I'm going to put a 2 over here, then we'd have 2 times 2, which is 4, plus 1, which is 5. Again, we would have 5 on this side and 2 on this side, and we wouldn't be able to put a number over here to make the reactants equal to 5. So a good strategy for us to use for this example is to make the number of oxygens even, and we would do that by taking a 2 and putting it over here. Okay, so at the moment we have 2 on the left hand side or in the reactants and 2 on the products. Now, because I've done that, I've made 2 zincs as well. So I'm going to fix that and make 2 zincs on this side. But because I'm putting a 2 here, it's going to affect the sulfur as well. So now I have 2 sulfurs on this side. Then I'm going to fix that by putting a 2 on this side. Okay, so let's just reevaluate. I have 2 zincs on either side. Great. So the zinc is looking good so far. But because I put a 2 over here, I have 2 sulfurs on that side. So I had to put a 2 over here. Now I also have 2 sulfurs. Now the last thing to do is to check out the oxygen. So you can see here the rule does work out. We are balancing oxygen last. We are finishing off oxygen last. So I have 2 oxygens on the left. That's still right. And over here I have 2. Okay, 2 oxygens over here and 2 times 2, which is 4. So I have 6 oxygens over here. And what do I need to do in order to make this side also equal 6? 2 times what gives me 6? 2 times 3 gives me 6. So if I put a 3 over here, I now have 6 oxygens on that side. I have 6 oxygens on that side. Everything else is balanced. Awesome. So going back to my tips, these can be helpful. If you guys want to see more videos of me balancing, I have tons of more equations. There's this one. There's this one. This one is an interesting one, by the way, and there's a special teacher tip that goes along with this one. Let me know in the comments down below, and I hope to see you guys in another video soon.